This is part 5 on our series on how to show video on the Commander X16. Now I'm going to try and do this a lot faster because I only got a little bit of part 4 done last time in part 4. So this is the rest of it's in part 5. Now we've got a few more file handling subroutines to write. We've got to save the default palette because we can't just simply read out of VRAM and save it. That's too easy. We have to do something a little bit different. And we got to set up all of our interrupt subroutines. So the first thing we have to do is the default palette. At the end of our our video, we want to reset this palette because we're going to be changing it every frame. So we've got the default palette listed here, but it's not in a format that it's easy to store in memory. So what we're going to do instead is we go to the 8-bit coding blog, and he's got the default palette of the Commander X16 listed here. And all we need to do is just select all of this down to here and Control C to copy, and then we bring up our spreadsheet. And on the spreadsheet, what I've done here, I just pasted that right here. And so all these 4 columns are just directly pasted out of 8-bit coding blog. Now, if we go back here to the Vera Programmer's Reference Guide, we can see that the palette, scrolled up too far, the red value is all by itself. There's 2 bytes for every palette entry. It's the green, blue first, and then the red. Now, the red's all by itself. It's in the format we already need it to be in. But green and blue, we have to modify this a little bit. We have to take 16 times the green and then add blue. So that's what we've done here in this column, green, blue. I've just taken whatever is in the green column, multiplied it by 16, add blue. Simple and easy. So now we can take this column here, green, blue column, and this column here, the red column, and use that to create some basic data statements. So here's the first one. You can see all it does is just take one entry from the green, blue, and then one entry from the red, and one entry from green, blue, one entry from red, so on and so forth. So you can use the spreadsheet to generate data. So we can see that this one here will be going, we're going to be storing all of this data starting at 7000. So all I do is just grab all of this, Control C to copy. We'll go back here and Control R, Control V. We run that. If it get -1, that's success. Yes. So now we've stored our default palette starting at 7000. So we want to now load swars.prg, 8, 1. That's what we've been working on all this time. And we run. If we go to 7000, we can see, hit F3, there's our default palette. So now we want to save this. So I go to the end byte +1, 7200, and we'll just type fend here. That's file end. We go to the start and type FSTR. That's our file start. And now we got to look for our path here. Our file path is swars. So we save swars / we're going to call this palette FFFF. .dat. Yes, file saved. So now we can see we've got a pfff.dat right there, and it is 514 bytes, just like we expect. So good, we've got our default palette. Next, very first thing we should do next is reset our file start again. So this is our file start, and if we, next thing we got to do is go to 0B00. We've got a few subroutines that I've already written in here. So what these do is change the audio file name or audio file name, palette file name, or video image file name, depending on some values in zero page. So let's go to zero page, and I'll hit F4 here, and you can see I've added a few labels in here. So odd number, odd H, this is the low byte and high byte of the audio file number. PAL number, PAL H is the low byte and high byte of the palette file number, and vid number, vid H is the video image file number. So if we go back here, we can see it's loading the high byte first and then calling cat C. Cat C just converts the accumulator into 2 hex digits and stores them in X and Y. And then it stores those in some relative locations relative to the start of each of these strings. So at 7 and 8 it stores the high byte, at 9 and A it stores the low byte, and it does the same thing for A file, P file, and V file. So if we go to A file, we can see that if S at the start, the S at the start is 0, and we count to the right, then 7, 8, 9, and A are the numbers just before the dot dat. So whatever values are stored in 0 page then become converted into hexadecimal characters and then stored in these 3 files. Now there's one other file here. This one's different. This one here, we're not going to use 0 page as counters. We're going to use the file name itself as the counters. Now these are all in decimal rather than hexadecimal. So what we have to do is we're only ever going to increase the file number here. So we start with this one here. We increase this value, and if it reaches 3A, 30339 are the numbers 0 through 9. So if it reaches 3A, we know we've gone too far. We reset this one to 30 and increase this one. And if this reaches 3A, we've gone too far, reset it to 30 and increase this one. If it reaches 3A, we've gone too far, reset it to 30 and increase this one. And because we don't have 9,999 frames, this will never reach 3A, so we're done. So to do that, we'll just go back. No, we'll go to this one down here. And that's what this does, is just does a decimal increment on the file name of the bitmap. So that's good. Now, next thing we've got is our custom IRQ handler. So we're going to go to 0314. This is the interrupt request vector. So anytime there is an interrupt, the accumulator X and Y and processor status are pushed to the stack. The program counter is pushed to the stack, and then it calls whatever is stored at this vector here. And in this case, it's E034 is the normal interrupt request. So every time there's an interrupt, it calls this vector, then does whatever it needs to do during an interrupt, and then it calls a return from interrupt, and that restores the accumulator X, Y, processor status, and the address. So what we're going to do is we're going to modify this. If we go back down to our custom IRQ, when we're running this, we're going to be looking for the vsync bit. And so all this is going to do here, I'll bring up Vera's programming reference guide here. If we go right to the top, here's all of the ones that are involved with interrupts, and in particular it's the interrupt enable that we're going to be concerned with, and the interrupt service request. And in particular on the interrupt service request, it's this bit right here, vsync, which is bit 0 of this value. So 9F27 is our interrupt service request, and if we go into the metal editor help file here, we can see that I've already got a default label for that value here. So VISR is the default label for our interrupt service request. All we're going to do in our custom interrupt is load that value and store it in 0 page, and then jump to some vector. Now we don't have that vector set yet, And that's what SIRQ is about. Near the beginning of our program, when we're playing this, we're going to call SIRQ first. And first thing it does is it disables interrupts. It sets the interrupt disable bit. And then it loads whatever's stored right now at the IRQ vector, the low byte, and it stores it right here at the low byte of this jump vector. It does the same with the high byte of the IRQ vector. It stores it at the high byte of this vector. Then it loads the low byte of CIRQ, which is this memory location, and stores it at the low byte of the interrupt request vector, loads the high byte of our custom interrupt request vector, and stores it at the high byte of the interrupt request. So after you've called SIRQ, every time there's an interrupt, it will go to CIRQ first, and then it'll go to the standard interrupt request handler. At the very end of our program, we want to reset that. But first, you got to notice that SIRQ does not clear the interrupt disable bit at the end. So after you call SIRQ, interrupts will be disabled until you call the CLID function. So at the very end, we are going to have to reset that. We're not going to want it to go to our custom IRQ vector anymore. So we will load whatever is stored at this vector, the low byte and the high byte, and we store that back at the IRQ vector just like before, and finally we clear the interrupt disable. So let's test this by this little short program here. We set the interrupt, start the interrupt request, and then we reset the interrupt request. So let's execute test, and you can see that now the interrupt request vector has been stored here at our custom interrupt. And it is still stored there because we've reset it. So that's pretty much enough for this video, and I will see you in part 6.